Welcome to everybody, and especially to our guest, Mark McIntyre. Mark is an astronomer and astrophotographer living in Oxfordshire with his wife Mary and many cats. They met through astronomy and share a passion for the subject, which they try to pass on to everyone they can. They have a garden observatory, a second outdoor pier, and several scopes of various sizes and makes, as well as several meteor spotting cameras fixed permanently on site and feeding data to UKMON live. Sometimes Mary and Mark get competitive, but mostly it's fun being married to someone who's as crazy about the sky as he is. Mark first discovered a love of astronomy aged about 9 when his parents bought him a cheap 3-inch refractor with a wooden tripod and fork mount. It had a built-in Barlow that promised magnifications of 5,200 times, as if. He promptly dismantled the scope to find out how it worked and lost the Barlow. Without it, the scope was, of course, useless, so it got stuck in a cupboard and forgotten. It wasn't until he was 12 that he returned to it, by which time he'd lost the tube and tripod too. He found he could attach the objective and focuser onto a bit of 3-inch drain pipe, and by trial and error found the right length. He then nailed the fork onto a fence post, and with this monstrosity first saw Saturn and its rings, and was hooked. He's since upgraded a bit, and his and Mary's scopes live in an observatory apart from their 10-inch Dob, which is mounted on wheels and lives in a small shed in the garden. The observatory scopes are computer controlled, though he still spends time in the cold, getting things aligned and swearing at the computers when they go wrong. We bleed with you, Mark. Outside astronomy, Mark's a computer programmer, and he spends a lot of time tinkering with hardware and software. Present projects include a Raspberry Pi to download weather maps from satellites, running Linux on an iMac, and running Open VMS on both Linux, on the iMac, and on a Raspberry Pi. He also enjoys gardening, woodworking, carpentry, and vehicle maintenance, though, as we all find, he says with modern cars, it's hard to do much more than reset the warning lights. Renaissance man, the floor is yours.
Thank you very much. And it's lovely to be here. I don't still have that monstrous scope, unfortunately, but it was an amazing experience the first time I saw Saturn through it. I still have very fond memories of it. So I'm trying to make sure I'm sharing the right screen. Hopefully you can see the introduction page of my slideshow now, because I've lost visibility to Zoom. So, okay, so this evening I'm going to talk to you a little bit about meteor hunting. I want to talk about why meteors are interesting to us, what they are, and different ways of hunting for them. And I'm going to finish off, if we've got time, to talking a little bit about the Winchcombe event, which happened back in February, and which I'm sure everybody's familiar with. So Nick's very kindly done most of my introduction for me already, but just to, oh, by the way, that on the right there, that is a picture of the homemade telescope nailed to a fence post. That is the actual telescope. Yes, so it really does exist, or did exist. So as Nick said, I'm based in Oxfordshire where I live with my wife, Mary. I'm also the Meteor Section Director for the Society of Popular Astronomy. And I'm a member of the UK Meteor Network, UKMON, and of the Global Meteor Network, which are video detection networks that I'm going to talk about a little bit later. Before I start, I'm just going to very quickly plug this. I'm sure you know all about this already, but as part of World Space Week, there is an event happening tomorrow in Guildford Town Centre. There are going to be all sorts of events going on in the town centre, and amongst other, not tomorrow, I beg your pardon, the weekend, and amongst other things, my wife Mary is going to be doing an astronomy sketching workshop in the shopping centre from about 10 till about 4, I think. And so if you're in the area, do drop in and say hello, have a go at some astronomy sketching. She's a fantastic teacher. She does this workshop quite a lot at things like Solar Sphere and various other outreach events, and she'd be delighted to see people. So there's an opportunity for you to see her and tell her how rubbish she thought my talk was. Anyway, so like I said, I want to talk about three things this evening. What are meteors? Where they come from, how they're made up, that kind of thing. Why they're scientifically interesting to us, and how we observe them. And that's going to cover visual, photographic, radio, and video observations. So if I start off with what meteors are, I'm sure you all know a lot about what they are. So obviously they're space dust. They are primarily fragments of asteroids that by and large date back quite a long way, right back to the beginnings of the solar system. Now, nowadays, if you go and stand in the asteroid belt, you stand on one asteroid, you are unlikely to see another asteroid. They're millions of kilometers apart. But of course, back in the beginning of the solar system, it was a much busier place, as this incredibly accurate scientific reconstruction of an flying through an asteroid field shows. Asteroids were much closer together, impacts between them were much more common, and those impacts create dust. Also, I don't think that very much of the asteroid dust was created by Han Solo shooting asteroids as he tried to evade TIE fighters. But these collisions obviously, as I said, created a lot of debris and dust, and that debris and dust is what we now experience today, as the majority of the meteors that we experience here on Earth. Most sporadic meteors are dust debris from asteroid collisions dating back millions of years. And for some reason, that always plays that page twice. There are other sources, of course, of meteors that we see in the sky. A few are bits knocked off other planets. And sticking with the Star Wars theme, here's a piece of Vesta. It's actually Tatooine, which was is a town, I think, in Africa, near where this piece of Vesta was found. And so obviously there were collisions between planetesimals and planets back millions of years ago, and that also kicked up debris, which sometimes forms meteors. This is a picture of an impact crater on Mars. I think it's Argyre Planitia on Mars. It's about 1,000 kilometers in diameter and about 5 kilometers deep. That's obviously a colossal impact. And as well as all of the pieces that obviously rained down and formed those secondary craters all around the main impact crater, a lot of the material from that would have been thrown up into space. And some of that over the subsequent couple of billion years has found its way to the Earth. And so we have little specimens like this tiny piece of Mars that's in my collection. It's about the size of a grain of salt. How do we know it comes from Mars? Well, I'll come on to that in a little bit, but essentially we do chemical analysis on it. And obviously, we also know by looking at the moon, we can see the moon has also been bombarded, and many of those bombardments threw material into space, some of which we found on Earth. And again, we know that that material came from the moon because we've got samples that the Apollo astronauts brought back with them. We can do chemical analyses and compare the two, and we can say to ourselves, yeah, that's a piece of the moon that we found in Antarctica or wherever it might have been found. Up until quite recently, we obviously couldn't do the same thing with pieces of Mars. So what we were doing when we looked at Mars or Vesta is we were inferring that information from spectroscopic studies of the planet by and large. Now, of course, we have first-hand experience of some of these places, and we can actually get a better idea of the origins of that material. Meteor showers are a little bit different again. So meteor showers, there are about a dozen or so major meteor showers every year, and there are many, many minor ones. I think there's about 300 at least in the database of minor showers. There's actually one in progress at the moment. The southern Taurids are going on right now. These meteor showers are mostly cometary in origin. This is a picture of a comet I took last year, naked eye comet that I took last year. And in this picture, you can see two tails. You can see an ion tail and you can see a dust tail. And it's the dust from that dust tail that creates meteor showers. Because comets have periodic orbits, they're going around the sun in pretty much the same location every time they go around. That dust accumulates in the orbit. And if the orbit of the Earth happens to intersect that dust trail, then we'll get an enhanced fall of meteors during that period, and we associate that with a meteor shower. So, for example, the Eta Aquaria is a debris from Halley's comet. The Perseids are debris from 109P Swift-Tuttle. The Geminids, which happen in December, are debris from 3200 Phaethon, which is technically an asteroid, but which we think probably is an extinct comet that's boiled off all its volatiles. Interesting enough, research suggests that the Geminid meteor shower is probably going to die away over the next few hundred years because there's no more new material being deposited into that meteor, that dust trail. The comet is extinct. And so as Phaethon goes around, it's not dumping any more dust. And so eventually over the next few hundred years, the Geminids will fade away. And actually what's currently one of the brightest meteor showers will be gone. Not in our lifetimes, but in a few centuries perhaps. And again, I'm sure you all know this already, but meteor showers are named after the radiant, which is the point on the sky that they appear to come from. So the Perseids, for example, appear to come from a point in the constellation of Perseus. Geminids appear to come from a point in the constellation of Gemini. That's just a line of sight effect. That's just a part of the sky that happens to be in the direction the meteor shower is coming from. So in much the same way that if you're looking out the window in a car, you might see the rain going past you in all directions. It's coming from in front of you, but it looks like it's coming past you to the sides. That's a line of sight effect. Another few facts that I think are always interesting about meteors. They're going very, very fast. As it says here, meteors are entering our atmosphere something between 20 and 80 kilometers a second. And that is pretty speedy. That's 50 to 300,000 kilometers an hour. Meteor can get from here to the moon in an hour. A meteor can get from me to you guys in a second. And because of that enormous velocity, despite the fact that they are very small, when they hit the atmosphere, they create a lot of heat and light. They all pretty much burn up entirely. The vast majority of meteors that you see in the sky weigh much less than a gram, and they burn up entirely in the atmosphere as they re-enter. All that's left of them is dust that falls to the ground over the subsequent few days and weeks. Some meteors, you'll actually see them leave a trail behind. You'll actually see what looks like a trail of smoke left behind them as they pass through the atmosphere. And again, that's that material that's left behind after they evaporate away. And sometimes you hear a noise. I've never actually heard a noise myself, but I know people that have said they've heard noises from meteor showers. And you would expect to hear a noise from something like a fireball. I think earlier in the year, there was a fireball over Dorset, I think, that people reported hearing. And I think there may have been one over South Wales as well that people reported a noise from. So it does happen sometimes. And altogether, all of this dust and that debris accumulates several thousand tons landing on the Earth each year from space, which is a pretty amazing number when you think about it. But the vast majority of that is tiny fragments of dust, smaller than a grain of rice, way smaller than a grain of rice. I'll talk a little bit about meteorites as well, and I'm sure you know the difference in a meteor and a meteorite, but meteorites are things that have landed on the Earth's surface. So the first sort of meteorite that you're likely to come across is an iron meteorite. They're about 5% of meteorites are iron. The majority of these, we think, are formed from the core of a planet that's been smashed up. So if you imagine something like a small planet that formed in the early solar system, may have had a molten iron core. It was then in a collision with another planetesimal, smashed up. The iron from the core of that planet may have formed an iron meteorite that we can collect today on Earth. Iron meteorites tend to be very hard and dense and heavy. And a lot of people think that these are the most common meteorite. They're actually not. There was online recently, there was a discussion with somebody who had found what they thought might be a meteorite. And to test that it was a meteorite, they hit it with a big hammer. It didn't smash up, and therefore they thought it must be a meteorite. Now, the first thing I would say is, if you think you found a meteorite, please don't hit it with a big hammer. Most meteorites are really fragile. And the Winchcombe meteorite, as you probably know, is extremely fragile. And if you hit it with a big hammer, you're just going to destroy it completely. This is not a good test whether it's a meteorite or not. But Stony-Iron meteorites, can be pretty dense and pretty tough. The second sort of meteorite, the second grouping, is Stony-Iron meteorites. And as the name suggests, these are made up of a mix of stone and iron. Again, going back to that smashed up planetesimal, if you imagine you've got a molten iron core and that's surrounded by rock, we believe that Stony-Iron meteorites formed at the boundary between the two, where the rock and the iron were mixed together. My cat has just come to join me, so apologies if you see a cat's tail waving in the air any second now. So Stony-Iron meteorites are the next category. But you notice that between the two of these groups, they're only about 7 or 8% of all meteorites that we discover. The vast majority are stony meteorites. And Again, stony meteorites are divided into three groups because scientists love three for some reason. And so one group of meteorites that you get is achondrites. Achondrites tend to be parts of planets. Earlier on, I showed you a piece of Vesta. That's an achondrite. They come from the surface of Vesta, the Moon, Mars, other asteroids, that kind of thing. Second grouping is chondrites. This is an example of a chondrite. This is a piece of Chelyabinsk. These are the oldest groupings of meteorites. These are all about 4.5 billion years old, and many of them date back to before the planets formed. And these are really scientifically interesting to us, as I'll explain a little bit later. And they contain a mixture of material, one of which is something called chondrules, which are little molten spheres or previously molten spheres of material. And that's where they get the name from. And the third group, of course, is the carbonaceous chondrites, which are similar to the chondrites, but they contain carbon compounds, organic compounds, and they're extremely interesting to us scientifically. And they're actually also the rarest sort of meteorite. I've talked a little bit about meteorites and meteors. I ought to mention the third group of objects that fall into this category, which is the meteoroid. The meteoroid is the name that we give to the piece of rock or piece of dust before it enters the atmosphere. So when it's floating around in space, it's a meteoroid. When it hits the atmosphere, it's a meteor. When it hits the ground, it's a meteorite. And this is one of the Winchcombe samples that I'm sure you've seen many times before now. This is in the Natural History Museum now, this piece. So I've talked a bit about what they are, and in that I mentioned some of the scientific research that we can do on them. So what can they tell us? So the first thing, obviously, that they can tell us is a lot about the origins of the solar system. Meteorites often contain material which dates back to before the formation of the planets, some materials pre-solar. And those pieces of material can tell us a huge amount about what was going on in the early solar system when it was forming. This is a picture of a protoplanetary disk. This is a real picture of a protoplanetary disk taken by the ULMA telescope, I think in the infrared. And if you look at this picture, you can see that the protoplanetary disk is divided into different zones. There's different temperatures. There's probably different chemistry going on in those different zones. And by studying meteors and meteorites, we can start to understand a bit more about the chemistry of what's going on there. So if you look at this slice through a chondrite, you can see that it's made up of lots of different materials, the different colors, different textures. Some of them look like they might be see-through, some brown bits, some dark bits. Each of these is formed in different conditions in the solar system when it was being born. And then they've agglomerated together to form a kind of rocky material, probably as part of an asteroid. And then that asteroid has been smashed up and the pieces have made it to here on Earth. But by studying the chemical composition of those, we can understand the conditions of the early solar system. And that might even give us some hints about the origins of life on Earth, because we know that early in its history, the Earth was bombarded by material from the outer solar system, a mixture of comets and asteroids. And that probably delivered a lot of the water to the Earth. And it may have delivered organics as well. I've said to you a minute ago that carbonaceous chondrites in particular have organics in them. And so by studying this material, we can maybe understand a bit more about the origins of life too. The other thing that obviously we can learn from studying meteors and meteorites is what the planets are made of. You know, I was saying earlier on that when we look at a piece of Mars, a piece of meteorite from Mars, we're slightly guessing that it's from Mars. You know, until we actually go to Mars and pick up samples of rock from the surface of the planet, we don't really know what these things are made of. We can carry out spectroscopic studies, of course. We can look at the light reflected off the surface of Mars or the Moon, but the atmosphere of the planet might interfere with that. There might be other things going on that we aren't aware of. And so by studying the rocks that land on the Earth, we can learn quite a lot about the structure and the composition of these outer planetary bodies. And I think what's interesting is to compare what we have got. So this is a sample of the Winchcombe meteorite. It looks like a bag of coal to me. And that's the kind of material that you might find from specimen on Earth. This picture is a picture of the sample return mission that went to the asteroid Ryugu and brought a sample back to Earth last December, I think it was. And you can see immediately how similar these two samples are. They both look like a sack of coal. But that's actually really interesting for us. That tells us that the models that we we've made based on studying samples like the Winchcombe meteorite are probably not far off wrong. You know, we look at what we've got from the asteroid Ryugu, and we can now start to compare these two. Now, sending a sample to every asteroid is impossible, but by studying the specimens that we find on Earth, we can make some reasonable assumptions about what's going on in the asteroid belt, what they're constructed out of, the chemistry, how they fit together, what keeps them together, all these kinds of things. And in fact, we have an amazing opportunity here. Ashley King from the Natural History Museum, who's working on these two specimens, was really happy that he was in a position to be able to do this, because he's now got two specimens from different places, but that he can study simultaneously and understand, you know, what's the same, what's different, what have we missed by studying the material we've got so far. So we can learn a lot about the structure of other planetary bodies by studying the material that we find here on Earth. And the third thing that's very interesting for us, and that we would probably like to know a bit more about, is what is the risk from these things? We all know that there was an asteroid that wiped out the dinosaurs. Well, it was one of the factors that probably wiped out the dinosaurs. But throughout the history of the Earth, we've been bombarded with objects from space. This is a picture of a couple of impact craters, I think, in the Sahara Desert. And these are pretty big structures. I mean, they're several kilometers in diameter, I believe. And the impact of that size would have thrown up a lot of dust and debris. And obviously, if it had happened directly over a populated area, it would have been devastating. And we'd really like to know more about whether there is a risk of these kinds of objects hitting the Earth. Now, we can do all sorts of studies, but one of the studies that we can do is to look at the meteor showers that we see in the sky. And how does that work? Well, let's take the southern Taurids as an example. The southern Taurids, which are going on right now, which I mentioned earlier on, have a parent body, which is 2P Encke. That's a comet. But there is some research that suggests that 2P Encke is itself part of a larger body that was destroyed in an impact many billions of years ago. Because the comet, these bodies are in a resonant orbit with Jupiter, they tend to be shepherded together. So if you look at the diagram on the left here, the Earth's over in that green circle on the left. The big oval orbit, that's the orbit of the southern Taurids, and somewhere out near Jupiter, there may be a collection of other material from the impact that created Comet Encke, which is trapped in a resonant orbit by the effect of Jupiter's gravity. But some of the pieces of that could potentially be knocked out of that resonance and come into orbit around the Earth, or hit the Earth even. And so by studying the southern Taurids and understanding how the orbits of the southern Taurids have evolved, the material they're constructed from, how things have changed for them over the decades that we've been studying them, we can start to understand a bit more about the risks that there might be from bodies like this out there somewhere in the outer solar system that we can't see visually, but which we can infer from studying the showers like the southern Taurids. So this is a very interesting thing that we can do with this kind of material. So that's a bit of a whistle-stop tour through what meteors are and what we can do by studying them. But how do we observe them? And I'm going to start off by talking about visual observing. It's not so long ago that Mary and I were sat outside in the garden observing the Perseids. For first time in many years, we've been able to do that without getting blown away or drenched, which was really nice. And what equipment do you need to sit out in the garden and observe a meteor shower? Well, you need a comfortable chair that you can sit and lean back in. I use a garden recliner. And the reason that you want something like this is you want to be looking up at the sky. You don't want to be tipping your head back for hours on end when you're staring up. And you're going to need to wrap up warm, because even in the middle of summer, it gets very cold at 2 o'clock in the morning. Don't underestimate how cold you'll get when you're lying still in a garden for a long period of time. And also a notebook or clipboard to record your observations. And I'll talk a bit more about how you can record the observations in a moment. In terms of which way to look, a lot of people think that the best thing to do is to look at the radiant, but that's actually wrong. If you think about you're trying to spot an aircraft in the sky, if the aircraft is flying straight toward you, it's a tiny target. You can't see very much of it, and you certainly can't tell which direction it's flying in or how fast it's moving, because all you can see is the front end of it. On the other hand, if it's moving across in front of you from side to side, you'll get a much better idea of how fast it's going. You can tell exactly which direction it's traveling in, and it's just the same with meteors. So when you're meteor hunting, look off to one side, about 45 degrees away from the radiant, look about halfway up from the ground to the zenith, and then just relax. Let your eyes get used to the dark. Maybe defocus your eyes a little bit so you feel like you're looking at a larger part of the sky, and just lie back and enjoy the sight. In terms of recording, the way that I record is very, very simple. I have a plain notepad. I'll write the meteor shower, the date and the time that I started observing at the top of it. And every time I see a meteor, I just make a mark on the page. Now, if I'm looking for something like the Perseids, I'll just draw a line every time I see what I think is a Perseid. If I see something that I don't think is a Perseid, I'll write S for sporadic. Or if I'm feeling really adventurous, I'll write a letter for the meteor shower name. So we saw a few Kappa Sigmids when we were looking at the Perseids, so I'd write a K for each one of those. And every hour, I would start a new page on my notebook. I use the clock in the village to tell me when the hour has passed. There's other ways you could do it. If you're going to use a mobile phone, do remember that your phone is probably going to turn the screen on when the alarm goes off. So you might want to do something different in terms of timing. But, you know, some means to tell when an hour has passed, just turn the page over, start a new page. And then at the end of the evening, you can go in and just count up how many meteors you saw in each hour of each type that you observed. You can get more adventurous if you want. On the SPA website, there is a form you can fill in to let you make other notes, like you can note how bright the meteor was if you're good at estimating the magnitude, constellation you saw it in, whether it was fast or slow, whether it was colorful, that kind of thing. But, you know, don't worry about all that. The basic information is just how many you saw per hour. And that's the key piece of information. If you do a meteor hunt, in, for example, the Geminids, which are coming up in December, I'd be very happy to receive a report from you. You can send the reports into me at meteor@popastro.com. I include details of all the reports in the section report that goes into the SPA magazine every couple of months. And there are also forums on the SPA website and on the UK Meteor Network website where you can report a fireball. So if you've seen a fireball, please do report that. These reports actually get sent to the International Meteor Organization, who collate them worldwide. So we get a picture of what's happening all over the globe. I want to talk next a little bit about photography. So I'm going to show you a few pictures in a minute. Mary's much better at the photography side of this than I am. But again, the essential equipment is a camera that's capable of taking exposures of between 10 and 30 seconds continuously. And by continuously, I mean you need to be able to lock the shutter so that you can set the camera up and just leave it all night taking pictures. You can have a lot of pictures in the morning to go through, but that's fine. You can sit there on breakfast thumbing through the pictures, identifying the ones that have got meteors in and saving those for later. A remote shutter cable or intervalometer will help a lot. Cheap intervalometer costs a few pounds off eBay or Amazon. And a sturdy tripod is a must. You need to be able to get the camera fixed pointing in one direction. You might also find a dew heater is very useful, and a bit of a plug again here for Mary. Mary did an article I think last year where she showed how to make a simple dew heater for a camera with an old sock and some hand warmers. And the article's available on the Sky at Night website. If you're interested in having a look at how that's done. And obviously, if your camera can take an external power supply, it's a good idea to use that. You don't have to, but if you do, if you can't change the battery or if you can't fit an external power supply, then obviously you'll have a limited amount of run that you can do on the Sky. And in terms of your camera settings, so 800 ISO or 1600 ISO is a good place to start. Start off with 10-second exposures. You may need to vary the exposure depending upon your sky conditions. We've got quite good skies here. We're about Bortle 4 skies here, but if you're in more light polluted sky, you might find a shorter exposure works better or a lower ISO. Just experiment a bit to get it right. Do a few test shots, point at a bright star so you can get focused. And then exactly as with visual observing, point 45 degrees away from the radiant, 45 degrees up, lock the shutter cable on and just leave the camera. Leave it running. Don't be tempted to move it around. Meteors happen all over the sky in every direction. No particular direction will see more than any other. So just leave the camera pointing in one direction. There's another reason for doing that, which I'll come on to in a moment. And then whilst your camera's running, you can sit back and do some visual observing. And effectively, you'll get twice as many observations for the price of one. Periodically, you can go back and check the camera hasn't fogged up, the battery's not gone flat, and that the focus is still good. But as much as possible, try to leave it alone. And what sort of images can you get? with just a DSLR. Well, here are a few of the ones that Mary took. This is a sort of fairly typical example of a meteor. Now, one thing I didn't mention a moment ago was framing. If you look at the picture, you can see over my shoulder, the person who's taken that, I don't think it's a real picture, by the way, but they've got some foreground objects to give you an idea of scale and to give you some kind of perspective on what you're seeing. And in the same way, Mary's put a tree in the corner of the shot here. So you've got some kind of foreground object to give you an impression of the size of the object on the sky. And also she's got a nice constellation on the right here. So if you want to think about framing your picture, that's always a good idea. And what's interesting as well is that even though we've got decent skies, you can see there's a lot of sky glow here, but the meteor shines through that. And quite often you'll see that even if you've got low-lying cloud or thin cloud, the meteor will show up through it. So don't be discouraged just because there's a bit of thin cloud. You can still take pictures. Here's another example. The framing was a little bit wrong on this. The meteor, unfortunately, is hidden behind the tree. But one thing you can see here is that there's a bit of color in the tail of this meteor. So the very end of the tail is a kind of orangey color. A green color, sorry, you've got a bit of orange in the middle. If you could see the head, it'd be a bit more white. And again, the framing here helps you get an idea of how big this object was on the sky. And this is an example of why I was saying keep your camera still. So this looks like a star trails. It's not actually a star trails, it's a sort of a star trail picture. What Mary's done here, she's taken 11 individual shots that she took with meteors in, and she stacked them all together. So if you look closely, you can see I can see at least 4 or 5 meteors quite easily on this picture. But it gives you quite an interesting effect. You've got a mixture of star trails and meteors. And if you leave the camera in one position and don't move it around, you can do this kind of thing with it too. And the last example I'm going to show you is a picture from a nice dark sky site. This was taken from Bulthwells in Wales when we were at Solosphere a few years back. This is a Perseid meteor. Again, we've got some foreground objects that give you an idea of scale. There's a nice plow in the foreground as well. And this was a big meteor. You can see from the size of how big this must have covered on the sky. And again, there's color in here. You've got green at the tail, you've got a bit of orange in the middle, white at the front end, and you can see the meteor breaking up at the front end as well. And so these are the kind of pictures that you can take. It's just patience, really. You just need to set the camera up and leave it running, and it will, hopefully, you'll get something like this out of it. Pace the weather, of course. And talking of the weather, I wanted to talk a bit about radio observations as well, because this is something else that is very interesting. Now, when I talk about radio astronomy, people immediately tend to think of Jodrell Bank or Arecibo or some kind of gigantic structure. But in fact, you can do radio astronomy of meteors with much simpler equipment. We're very lucky here in the UK in that we have about 700 miles to the south of us, there is a massive radar station in France at a place called Grave. And that's actually a space defense radar station. So it's pointing a beam of radar up at the sky constantly. And when that beam of radar hits the ionization trail left behind by a meteor, because obviously meteors get very hot as they're passing through the air, the radar is reflected off that meteor trail. And we can pick that up in our homes with a very simple antenna made out of some old copper pipe and some wood. Here's actually a picture of mine in my loft. You can see it's a simple Yagi antenna. If you're not sure what a Yagi antenna is, that means it's got a number of horizontal bars which are acting as radio reflectors and intensifiers. And that's connected to an aerial cable that runs down to a little USB dongle that's plugged into my PC. And then I'm running some free software on the PC, which detects those radio reflections that you can see at the top there and turns it into a sound. And I'm hoping I remember to turn sound on my Zoom connection before I started this session, so you can hear what that sounds like in a second. So this is, hopefully, at least, this is what it sounds like when one of these reflections happened. So hopefully you heard a hiss and then a whistle there. If not, I really apologize. It means I forgot to turn sound on, but I'll play it again. So you hear the background hiss, and then you hear a whistle, and that whistle is the reflected radio waves being Doppler shifted because the meteor is going so fast. That's the most basic thing you can do with this, but you can also create a heat map. And what is a heat map? So if you think back to when you were doing your visual recording, you were making a note of how many meteors you saw each hour. Well, a heat map is exactly the same thing. So this is an example of a heat map from the Geminids last year. And what we've got here in each of these boxes on the diagram on the right is the number of meteors that the radio detector picked up in each hour of each day that I ran it. So I run my detector constantly. And so you can see, well, nearly constantly, I think it crashed a few times, but you can very clearly see when the Geminids happened. And actually, this is really interesting because sometimes you pick up new meteor showers like this, and sometimes you pick up interesting events. So the Perseids this year, this normal peak happened, but there was a secondary peak, which was predicted by meteor scientists. They predicted there'd be a secondary peak the following day, around about noon to 2 o'clock in the afternoon, I think. And we were able to pick up that peak on our radio detector and confirm that it had happened. And this is why I mentioned radio earlier on in conjunction with weather, because the great thing about radio is that you can do radio detection even when it's raining. You can do it during the day, during the rain, snow, hail. It doesn't matter. Your radio detector is safely indoors and it works during all weather conditions. So I actually run mine 24/7 up in the loft. The aerial's up in the loft. The receiver is behind my desk here. And this is another example of a heat map. This is actually from the Perseids last year. And again, you can see quite clearly when the Perseid happened. We were detecting up to 40, 45 meteors an hour during that peak period. And then there's a background noise level of about 5 or 10. This heat map, by the way, shows something else very interesting. You'll notice when you look at it that the top half of the graph is more yellow than the bottom half. So the meteor count in the top half is higher on average than it is in the bottom half. And this is a real effect. If you imagine that you're out walking in the rain and the rain is blowing in your face is going to get wetter than if you turn your back on it and face the other way. And we're getting exactly the same effect here with a meteor shower. A meteor shower is coming, streaming in from the outer solar system. The Earth is moving toward that meteor shower, then moving through it. The part of the Earth that is facing toward the outer solar system, so the night side of the Earth, gets more meteors hitting it. And so we're picking up that effect on our radio here. We're seeing how there's a diurnal effect. The side of the Earth that's nearest to the sun gets fewer meteors because they've been soaked up by the other side. In just the same way that you get wetter when you're walking into the rain than when you're walking away from it. I think it's very interesting. As I said, one of the great things about it is you can do it during daytime. So this is a method that we use for detecting meteor showers that happen in the spring. A lot of meteor showers in the spring are daytime showers. Their radiance are too close to the sun for us to detect at night. And so we use radio to detect those. I'm going to come on now to talk about video observing, which is probably my current passion and where I spend most of my time, too much of my time, I guess. So this is very interesting. When I first got into this a few years ago, it was a pretty expensive business. To do video detection of meteors, you would normally need quite an expensive high-end security camera. Very light sensitive security camera. You would need expensive software. There's only one company in the world made the software that we used. That was a Japanese company. And you would need a reasonably powerful computer to run it on. So adding all that up, you would be spending, well over £500 on a system to capture video meteors. So putting 2 or 3 of those cameras in was starting to get very expensive for people. However, there's been a revolution recently. In the last, I guess, 5 years or so, the market has been flooded with very cheap security cameras, very cheap, very sensitive security cameras, which are much, much smaller. Oops, I've gone the wrong way. So that's an example of one of the new security cameras that we now use. It's a tiny little module, only about 2 inches square and a couple of inches long. But these cameras are at least as sensitive, if not more sensitive, than the cameras we were easily spending £150 to £200 on a while back. The software too has been revolutionized. We're now using open source software written by Python in Python. The software has been written by a combination of professional meteor scientists working at universities around the world and amateurs like myself who are contributing to the project. And as I said, it runs on a Raspberry Pi, and in real time, it detects meteors and stores data about them. And so we're running these cameras every night. The whole, an entire kit now costs about £200 to buy, or you can make one yourself by buying the parts and assembling it yourself. Excuse me. The software captures the meteors overnight, and then in the morning it reanalyzes all of the data to try and reject as many of the clouds, bats, birds, aircraft, satellites, etc., as it can. And then the data is uploaded to the Global Meteor Network and the UK Meteor Network servers, where we do matching analysis on those to try and calculate the orbits and trajectories of the meteors. And if it was a very bright event, it was a fireball or something that might have led to meteorites on the ground, we'll try to estimate its landing zone as well. And the technology to do that is now well within the grasp of amateurs. And we've got, I think, about 50 or 60 members now in the UK Meteor Network and over 100 cameras all over the country, which are contributing. And it's a fabulous example of pro-am collaboration. That's a picture of a couple of my Meteor cameras on the outside of the shed. I'm sure our neighbors think we're insane, by the way. We've got 5 security cameras on our observatory, but they all point at the sky. It's as though we're expecting aliens to come down and steal our telescopes. But on the plus side, we've never had anybody try and steal anything. So I guess it's working. So what can you get out of these cameras? Well, I'm going to show you this first. This is a stack of every detection that one of my cameras made in one night back in May. And this looks pretty messy. You can see a lot of cloud. There are lots of aircraft in this picture. There are also lots of satellites. There are, in fact, also some meteors, although you might struggle to pick them out. However, this is before the software does its job, and this is after. So you can see immediately the software has eliminated almost everything that wasn't a meteor. There are 1 or 2 aircraft left in here. And I went and looked at that, and I realized that those aircraft are in the same frame as a real meteor. And so the software has left it in because it's in the same frame, but in fact, it knows it's not a meteor and it's going to ignore it later on. So that's the kind of cleanup job that they can do. They can take that very messy picture full of rubbish and they can turn it into an image with just the meteors that we're interested in. And that's a great result. The software also generates some very interesting maps. This is a map of the whole of the sky, showing you the red lines are each of the meteors that were detected. This is a different night in April, so during the Lyrids. Each of those red lines corresponds to a meteor. The yellow dot that you might just about be able to make out at one end of it is the lowest point on the meteor. And going back from each of those red lines, there is a faint line that is forming a great circle. And if that great circle intersects with the known radiant of a meteor shower indicated on this picture by the green, orange, and blue circles, then the meteor can be tentatively assigned to that shower. So this lets us very quickly determine whether we've picked up any shower meteors and gives us an indication of the activity that we've seen in the night. This is all happening on the Raspberry Pi. So this is all data you can get out of your Raspberry Pi. There's more data you can get out of the Raspberry Pi as well, though, and I'm going to just come on to that now. This, by the way, is a stack of every event that happened during 1 month earlier this year, just to give you an idea of how many meteors we're seeing. And in fact, recently I've had 100 meteors on each of my cameras in a night, and we're not even in the middle of a meteor shower. During the Perseids, the UK Meteor Network collected 16,000 orbits in one night, 16,000 meteors, sorry, in one night, and nearly 3,000 orbits. And that's a phenomenal achievement for an amateur network of just people like you and me with something stuck on the outside of our observatory or house. You can also generate movies of the detections you've captured. And there's a couple of things that are interesting about these. I mean, the first thing that strikes you about this picture is there's a lot of cloud. There's a lot of cloud in this picture. And yet we still detected, I think, about 30 meteors this night. And you can see them moving across your screen, hopefully, as long as my internet doesn't glitch too much. And one of the great things about these security cameras is that they are very infrared sensitive, and that means they can see through the clouds. I find these images very useful, by the way, for outreach purposes. They're quite mesmerizing sometimes to watch. And so you can generate this kind of data that you can share with people. You can also generate an all-night time lapse. Now, I find these absolutely fascinating. They're actually very useful as well. Typically, Mary and I will watch the time lapses in the morning to see if we've got any exciting fireballs or anything that's worth investigating further. But the software basically is recording all night. So in the morning, it can generate a complete all-night time lapse showing everything that's happened. There's just a meteor flashed there. I think there's quite a few flashing away in the background. You can see satellites, you can see aircraft, obviously you can see clouds bubbling up and down. I find it fascinating, by the way, watching the clouds. Did you see that? That was a Starlink pass going across one side of the screen. I'm not a fan of Starlink, but they do look amazing on the cameras. And so we can look at these time lapses in the morning and we can very quickly ascertain whether there are any interesting events that it's worth looking at a bit more closely. I'm just going to let this run to the conclusion because I do actually love these. They're absolutely mesmerizing to watch. I'd love watching the clouds bubble up and then evaporate away again. You always think of clouds as being quite static, but when you see them in this, you realize how they just come up from nowhere and then disappear again to nowhere in a matter of minutes. Dawn is going to break shortly. I think we might get a few more meteors coming in there, and I think, if I remember rightly, we got clouded out just before dawn. So I think we're about there. But yeah, the cameras generate this kind of time lapse every night. And then in the morning you can review them, which is great fun. So that's all stuff that happens on the camera or on the Raspberry Pi, and that's all stuff that you can access very easily and share. Whoops, let me just flip to the next page. We can also, of course, do more scientific analysis. Now, I mentioned before that we've got lots of cameras and with different viewpoints, and if two cameras pick up the same meteor, like, for example, these two pictures here, these are the same event seen from two different locations. We can do further analysis. I'll just quickly mention that top picture, what looks like a giant space octopus reaching out across the picture. That's actually birds. This picture was quite close to dusk, I think, and the birds were flying quite high. And so their wings were reflecting sunlight back down to the camera. And that shows up because the camera takes effectively a 10-second exposure. Excuse me. You get these kind of weird tracks that appear on the image. Fortunately, the software knows all about that and gets rid of them. But we can take those two meteors and we can use some geometry to work out, for example, the orbit of the meteor. And I think that's an amazing thing to be able to do just with amateur equipment. So here we've got details about the orbit, how fast it was going. We can estimate the magnitude and the mass, and we do that by looking at how bright it was. There's a kind of a formula that estimates the mass of a meteor from how much energy it gave off as it burned up. And so we can estimate its mass and its magnitude. We can work out how high it was when we first observed it and how high it was when it burned out. And we can also work out its track across the ground. So this particular meteor was traveling east to west across the English Channel. The three crosses, or the crosses there, represent the stations that detected it. And if that had been a bigger event that had reached a lower altitude, maybe we were thinking it might have fallen somewhere, and it had happened over land, then we'd have an idea of where to go and look for meteorites that might have reached the ground, which of course is exactly what we did with the Winchcombe event. So we can generate all this sort of analysis from the cameras. And in fact, we run something on the UKMON website every night where we generate this data for all of the events that we've captured. And there's other analysis you can do with the data. So this is showing you the number of Lyrids that we detected in 10-minute intervals over 5 nights during the Lyrid shower last year. And this helps us identify when the peak of the event was very clearly. We can look at the magnitude distribution of the events. We can look at where the radiant was. Now, I talked about the radiant earlier, and I think most people probably think that the radiant of a meteor shower is just a point in space. But actually, it moves, constantly moves every day. And that's partly because we are moving through the debris trail. And so the apparent point of that debris trail impacting on our atmosphere is changing as the days go by. And this picture here is showing you where the apparent radiant was on a number of different occasions during that particular shower. So there's a lot of interesting analysis we can do either automatically or manually from that data. We've also made discoveries from this data. So, for example, Paul Rogemans, who runs a similar network in Benelux, he and a team of guys worked with some of their data to identify an enhancement in the activity of a particular meteor shower. The guys in Japan who wrote the software that we used to use, they did a massive study of 10 years worth of data to identify a whole load of new showers and eliminate some that were duplicates. Another outburst that was discovered by looking at data from the Global Meteor Network and this network, and more recently, a brand new meteor shower was discovered by studying some of this data. The gamma draconids were identified by studying data captured by these cameras. And I think it's fantastic that we can genuinely contribute real science from this equipment that we're running in our garden sheds. Okay, I'm nearly finished, and I hope I haven't gone too fast. But before I finished, I thought I would talk a little bit about the Winchcombe event. Now, I'm sure you've probably heard most of this before, but it's always an exciting story. So a couple of years ago, myself and the other members of the UK Meteor Network had we have an annual conference get together. We had a conference in Cardiff, and at the conference in Cardiff, we invited Luke Daly from Glasgow University down to talk to us, and we invited somebody from the Natural History Museum to come and talk to us. And one of the topics that we talked about was, what would we do if there was a meteorite fall in the UK? And we realized we didn't have any idea. We had no protocol in place. We didn't know who to call. We didn't know what processes we should follow. We didn't know how to inform the public. We didn't have any idea at all. So we set up something called the UK Fireball Alliance. And the UK Fireball Alliance, the idea began 2 years ago, but in fact, it didn't really launch for various reasons. It didn't launch until last December. Luke Daly from Glasgow University, one of my colleagues from UK Meteor Network called Jim Rowe, and somebody from the Natural History Museum called Ashley King were got together to put that plan together. And to our absolute delight, of course, we were able to put it into effect almost immediately. When we picked up this amazing event on multiple cameras across multiple networks. In fact, you can see here that Global Meteor Network, the UK Meteor Network, FRIPON, which is a French network, Nematode, which is another UK network, and SCAMP, which is the UK outreach branch of FRIPON. We all detected it on many cameras. And the protocol that we put in place meant that we were able to quickly gather that data and send it to multiple teams for analysis. Now, I mentioned at the start of the picture that my talk that we can work out the tracks of meteors from looking at these pictures. Now, if you look at this particular picture here, you can see the path of the meteor on the sky quite well, because Richard Fleet, who took this picture, had a sideways on view. But if you remember the picture at the very start of my presentation, that's the same meteor, but seen nearly head on. My view was very different. And so in order for us to analyze that data, we have to do it manually. We can't rely on the automated systems because they will misidentify things when they've got those different angles. So all of this data was sent away and analyzed manually by 3 different teams. Their results were put back together and a kind of average result was obtained. That's another view of the same event from a different camera. This is a Nematode camera. And that allowed us to identify, within a matter of hours of the event, we were able to identify the strewn field, the area where we think those objects might have landed. And that's the picture I'm sure you all saw in the papers of the strewn field. But of course, because of COVID, we couldn't go and look for it. Now, I live about, I guess, 20 miles off to the right of that picture, easily within half an hour's drive of where this meteorite fell. And under normal circumstances, Mary and I would have been straight in the car, driving over there, carrying out a fingertip search of the fields, trying to see if we could find any objects. But of course, we couldn't do that. We weren't allowed to leave our homes at the time. So what happened instead was we ran a publicity campaign in the TV and press. My colleague Richard Kasharek, who's one of the founders of UK Meteor Network, was talking to the newspapers, he was talking to the radio. We were all writing newspaper articles and press articles. We were publicizing as much as possible what people should do if they found something, what to look out for. And I'm sure, as you all know, we were absolutely delighted when the next morning we did get the call from somebody in Winchcombe to say that they think they'd found something. And again, the protocol kicked in. We informed the Natural History Museum. They were able to get permission from the Home Office to send somebody from Oxford University to, actually not from Oxford University, from Oxford Open University, I think, to go and look at the fall. And this is the famous splat on the driveway. And you know, as I'm sure you know, in his own words, he opened the bag containing that material and his knees went weak because really this was the real deal. This was a genuine carbonaceous chondrite find, and it was a very exciting time. We actually knew the night before that it had been found. We weren't allowed to say anything. We were under press embargo for quite a long time, but it was a very exciting time for us. And then, of course, because we now knew that we'd found the real thing, we were able to get permission from the Home Office to send teams from all over the country to do a proper search. And so Luke brought people down from, I think, Glasgow, people came from Manchester University, people came from, I think, Southampton, and there were teams of people in that HIST as well. And over a period of a few days, nearly 500 grams of the meteorite was recovered from a number of locations, including various other specimens that I've showed you earlier in the talk. And that was a fantastic result, not just for our camera networks across the country, but also for the protocol that we put in place, which meant that all those networks were working together combining their data super duper quickly. I mean, literally within hours of this fireball being picked up on the cameras, we had the data in the hands of meteor specialists at the University of Ontario and in Australia and other places doing, manual reduction of the data to calculate the trajectory as accurately as we could. And in fact, some of the work that's been done has refined the processes that we now use, and typically we can now work out the location of a meteorite fall to within a few tens, hundreds of meters maybe. The strewn field for this one was pretty big because we were having to hedge our bets a lot. But a more recent discovery in Croatia, they managed to narrow it down to an area about the size of 2 football fields. Which is a pretty small area to search. There was a slight issue with searching it. Unfortunately, it turned out to be a minefield left over from the Civil War. So no recovery was found from that particular event. But the fact that this camera network can generate data that we can whittle down to that sort of small space, I think is amazing. What's happened with all that material now? Well, these specimens are now in the hands of science teams around the UK and in other countries, and different teams are specializing on looking at different things. Earlier on I mentioned how important the chemistry of meteors and meteorites is. Well, there's teams looking at that, the structure, the mineralogy, thinking about the origins. Where did this specimen come from? We know from looking at it, it looks pretty similar to Ryugu, the asteroid. Does that mean it's come from another asteroid? That would be really interesting to discover. They're looking at the organic compounds in it because it is carbonaceous chondrite, which is an incredibly rare thing. And again, one of the fantastic things about this is because the network kicked in so quickly and because the protocols worked so well, we found this material before any rain had fallen. We found it within a matter of hours of the fall, which means it's really pristine. It's in really good condition. And that means it's a fantastic scientific discovery. Earlier on, by the way, I showed you a slice through a chondrite in my collection. If you look at the picture on the bottom right here, that is a photograph of Ashley King's computer screen at the Nat Hist Museum. That's a slice through the Winchcombe meteorite. And you can immediately see the similarities and the differences here. There are chondrules. You can see those round blobs that look kind of transparent. There are dark patches, there are light patches. So there's a lot of similarities to the material in that specimen of mine. Mine is nothing like as rare, I should point out. But again, this is the kind of scientific research that we are now able to do with that specimen. And because we found it so quickly, it's in really good condition. And I'm really looking forward to the scientific research and the papers that are going to come out of this. We're going to be seeing papers coming out of this research for decades, I should think. And also, of course, we are now ready for the next fall. It was 50 odd years between this fall and the previous one. We really hope we'll find one sooner than that. We've got a lot more cameras now than we had back in February. Back in February had about 20 cameras in the UK Meteor Network. Like I said, we've now got about 100. And we're really hopeful that we'll find something else like this pretty soon, certainly within a few years. Cross fingers, touch wood, we'll hope for the best. There again, that's the specimen that I have in my collection, just again to show you the comparison between the two, which I think is pretty obvious. And so I'm just going to finish by replaying that video that kick-started the Winchcombe event. This is the Winchcombe meteorite happening. And I think it's an amazing video. And it's really interesting as well. You can see lots going on here. You can see the meteorite breaking up a number of times. There's a number of breakup events there. And each of those breakup events contributed to a different area where meteorites were found on the ground. And actually the analysis was able to track down some of those in quite a lot of detail. So although this is also a fascinating video, it also really helped us understand where we might be looking for specimens. And that's it. I've come to the end of my talk. If you're interested in knowing more about meteor hunting, there's information on my website. There's also lots of information on the UK Meteor Network, the Global Meteor Network, and of course on the POP SPA website, where I've got information about meteor showers, observing, recording, reporting your results, dates of all the meteor showers, information about the backgrounds to all the meteor showers, and so on and so forth. And so, if you're interested in any of this, then also you can get in touch with me, and I'll be happy to point you in the right direction. And with that, I'm going to stop. I've gone through that quite fast. I apologize if I've gone too fast, but I'm open to questions.
Mark, thank you very much. Usual thing, if you can put your questions up first by chat, then I can sort of cluster them so they're similar ones. And then a little later, we'll encourage people to ask questions direct. So please use chat. But Mark, that was an amazing tour de force. auteur and de force.
Thank you. I'm always nervous about going too fast because I do tend to talk fast when I get excited. And I find this subject very interesting. I think there's a huge amount of very interesting research going on here at the moment. And particularly with the video networks, there's a fantastic opportunity.
Don't misconstrue this, but your enthusiasm was palpable.
Good. And I should say, don't worry if nobody actually has any questions, because I obviously went through that quite fast and covered a lot of material, so I've probably blown people's minds.
I've got a question from Jonathan Shin. What is the mass distribution of the meteorites?
That's an interesting question. Do you mean, if you mean the ones that we have on the ground, the actual meteorites that we found, they do vary. Obviously, to find a meteorite, it's got to be beyond a certain size. Otherwise, you just won't be able to spot them. So the vast majority of meteorites that we have in collections, I think, are kind of pebble-sized to fist-sized rocks. I have to say, the vast majority of meteorites that we have come from Antarctica. We find them in Antarctica, and that's primarily because of the conditions there. They fall over the ice. There are certain movements that take place within the ice that tend to shepherd all the meteorites to a particular part of Antarctica where expeditions go out to find them. If a meteorite falls over the sea, it's lost. If it falls over forest or jungle or even farmland, it can be lost. So by and large, the ones that we have on the Earth tend to be fist-sized. When you're talking about the meteoroids out in space, the vast majority of those are tinier than a grain of sand. I was talking earlier on about the size distributions. I didn't mention there was a picture I showed in one of my slides where we saw a picture of a large number of meteors over one particular night. Now, the heaviest of those meteors weighed 1/100th of a gram. So the vast majority of them are very tiny. Even the brightest ones in the sky that we see, it's very rare for anything to weigh more than a few tens of grams.
Jonathan actually meant, what's the range that you detected and calculated?
Oh, right. Okay.
Network. The other was very interesting as well.
No, I don't think that we've picked anything up that weighed more than about a gram, other than the Winchcombe meteor. And there's a couple of reasons for that. Firstly, if it's heavier than that, the amount of light that it gives out will be so much that it floods the pixels of the sensor. And if that's the case, we can't properly estimate its mass. Now, we are doing some research to try and figure out a way to calculate the missing light effectively. You imagine, the light is forming a kind of the cross section through the light should be that, but it's been flattened at the top. So we're trying to estimate that missing bit by doing some sort of some scientific analysis of the curvature. But because of that flow, if you like, in how the process works, we can't properly estimate the mass or the magnitude of fireballs. And so we underestimate the mass of bright events, usually quite significantly. So for example, the Winchcombe event probably deposited about 1 kilogram of material on the ground, but the calculations would tell you that it weighed about 20 or 30 grams at the most. And the vast majority of detections that we have are a gram or less.
A question from Gordon Joy. What are the settings for your CCTV cameras on your shed?
So we're using an IMX291 security camera, which is capable of detecting down to, I think, 0.00001 lux. Now, that's difficult to translate into the kind of terminology that people are used to with DSLRs or cameras like that. So I would find it difficult to tell you, but the cameras can record video at 25 frames per second down to about mag 6 in my skies. Yeah. So that might give you an idea of the sensitivity. They are very sensitive cameras. And that actually is another reason why they're not great for fireballs, because they are so sensitive that a bright event like the Winchcombe event completely floods the sensor.
A question from Tim. Really good talk. Thank you, Mark. I wonder what your photographic hit rate is. DSLRs, I think. He has used a DSLR setup similar to what you showed, and over perhaps 3 hours of snapping, I maybe get nothing, maybe one not very impressive meteor. How do you do?
Yeah, I'm afraid you're right. That is quite often the case. One thing I would say is a lot of websites will advise that you use a wide-angle lens because then you'll get obviously more sky in. I don't think that's a good idea. And the reason I say that is a wide-angle lens does get more sky in, but the meteors will be much smaller on that field of view, and the faint ones are more likely to get washed out. Also, if you have too long an exposure, you'll get more background sky glow coming through, and that will also wash out the meteors. So you do have to experiment a bit. I think during the Perseids, Mary had a camera running. Now, during the Perseids, Mary and I visually saw about 80 meteors between the two of us over a 4-hour window. Mary had a camera running over that same period of time, and I think she picked up 3 or 4. So the cameras are less sensitive than the human eye to that sort of thing. But the key really is to adjust your settings. You'll have to experiment a bit really to get the settings right. You want the sky to be fairly dark, but you also want to be sensitive enough to pick up the meteors. I use my standard kit lens. It's a 55mm kit lens that I've got on the camera. Mary uses a prime lens, sometimes a 50mm prime. That is ideal. It's a f1.2 or something prime lens, so it's a good lens. But again, you know, you have to experiment a little bit. But you're right. You may spend all morning looking through pictures of nothing. But then again, you'll get 1 or 2, and it's worth it, I think.
From Mark, unfortunately, I think is that Mark Drazy, I think. It says, amazing talk, thanks, Mark. Has an origin point, a source, I guess, a source origin point for Winchcombe been found or suggested, i.e. Mars or the Moon? Or
we're almost certain it's asteroidal in origin. I don't think a precise trajectory has been calculated yet. There's nothing that we do have an orbit for it, but there's nothing obvious in the orbit that shouts out as being a likely progenitor body. You know, there's a lot of asteroids out there that we haven't spotted. It could be from practically anything, but we know it's certainly not from Mars or one of the big asteroids like Vesta, because the chemical composition of them is just wrong. This is a carbonaceous chondrite type. I think in that picture that I showed where I compared it to Ryugu, you could see how similar it was to the material that Ryugu is made of. A lot of asteroids are rubble pile asteroids, so they're just a big collection of you know, chunks of miscellaneous rock jammed together. That's the most likely kind of source, but we don't yet have a named progenitor. I'd love to have one, but not yet. Research is going on into this, though. Absolutely is going on into this, and we would certainly hope that we'll be able to identify something at some point.
Any other questions? If not, thank you, Mark, for a completely fascinating. I really am, like so many people, going to have to trawl back over the recording and work through it slowly. One last, there was a question. What was the software you were using?
It's called RMS, Raspberry Pi Meteor System. It's open source software that's available on GitHub, and there's a link to it on my website, or you know, I can send a link after the meeting to Nick, and he can circulate it.
And where's the best place to purchase the cameras?
Well, I would have to say the best place to purchase them is from the UK Meteor Network. You can buy all the parts yourself. We actually buy the parts from AliExpress. The cameras the cameras themselves are about £35 from AliExpress. You've then got to put them all together with the Raspberry Pi and configure everything. One of my colleagues in UK Meteor Network actually provides this as a service to build the camera for you. But if you want to do it yourself, you can do that as well. If you're interested in learning how to build them, then join our group on groups.io, UK Meteor Network, the group is called, on groups.io, because we have a parts list there, and the people on the group will be able to advise you on where to buy them and which parts you should need. And there's also an entry on the Global Meteor Network wiki, which I wrote a couple of months ago, explaining again the parts you need. So again, I can send Nick links to all that after the talk, and you can distribute them.
Thank you, Mark. Well, thank you. On behalf of GAS, that was excellent.
Absolutely.
Thank you very much. I'm glad you enjoyed it.
Anybody who gets to see Mary on Saturday, just say what a splendid talk that was. Thank you, Mark.